All right, thank you. All right, so I'm Mark Barnes from Los Alamos National Laboratory. I guess first off, I apologize. I have a bit of a cold, so I'm going to attempt speaking for the people in the back, but I probably won't succeed. Anyways, I'm very glad to be here. Obviously, things are in flux right now, but I was able to get my travel approved, and so I'm very excited to be here. So Los Alamos has a reasonably long history with open source. We have a lot of university academic collaborations, and so releasing our research software under a permissive license, we found it to be very helpful to foster collaborations and bring in students. So it's been a great value to us and a great value to the academic community as well. So what I'll be talking about here, I noticed there's been a good bit of energy analysis software. This is a little bit more specialized than some of the other packages we've seen. So this is a add-on package that's specifically focusing on the analysis and mitigation of geomagnetic events. So why do we care about them? As we've probably noticed, in kind of more casual reporting, there's a great variation in terms of predicted severity of events, and it kind of varies from, okay, not much will happen to, one hemisphere of the world is going to go back into the pre-industrial age. So how do we predict this? Will an electrified transportation network be completely knocked out? Will your phone explode in your face? I'll attempt to answer some of this, so let's dive in. Okay, so I apologize that like half of this presentation is background, but what's a Carrington level event? So this was a space weather event named after the British scientist Richard Carrington back in 1859, and this was the largest observed geomagnetic event, which fortunately occurred before there were continental scale interconnected power systems. We just had telegraph lines, which was enough to observe the effect, but sufficiently simple to not have a major impact. Anyway, so how do these work? So what we have is charged particles coming off of the sun. They get trapped in the Earth's ionosphere, or magnetosphere, and they form a net current flowing above the surface of the Earth through the electrojet. So this induces a magnetic field and in turn an electric field on the surface of the Earth, and this will couple into electric transmission lines. Now, what do these fields look like? So here's a measured waveform of round electric field from the Quebec March 1989 event, which was one of the more severe events of the last century. And so what we notice is the time scales on the order of about 1 second to 1 day in terms of variation. And the amplitude, if you're looking carefully at the y-axis, so this is on the order of volts per kilometer. So this is one thing that's good, right? So like even for your largest phablet, a field on the order of volts per kilometer is not going to make your Samsung Galaxy explode in your face, but it can still have effects on the electric power grid. So what are those? So over here we have a large power transformer. These are very big, very heavy, and very expensive. And for this reason, we operate them right on the edge of saturation. So that means that even for a not enormous additional current flowing through this transformer, we can put it into half-cycle saturation like we see on the figure here. So what's this mean? Well, this means that our transformer's exciting current has these big spikes in it. And these will introduce harmonics in the power system. Those can cause trouble. But the most significant impact is that there's a fundamental component of that current that's out of phase with the voltage. And this increases your so-called reactive power losses. And these can impact voltage stability on the grid. Also, we can experience transformer overheating as a result of local hotspots. Now let's go into how does computing impact power systems. So we've got a number of different analysis types. We've got transient solvers, steady-state solvers, dynamic solvers. But for a mitigation problem where we care about solving this in terms of optimization, typically we're limited to a steady-state solver. So modeling GICs in this context is a little bit tricky. This motivates our workflow that we hear here, suggested by the North National Electric Reliability Corporation. So we have a number of different steps. We apply Earth connectivity model, put it into a coupling model, apply a DC solve, apply our transformer saturation model, apply our AC solve, and then perform mitigation measures. Now, what does this look like in terms of circuits? So on the left here we have a positive sequence model where we represent a transmission system that's approximately balanced as one line. This doesn't work for quasi-DC current, so what we have is the model on the left here, which is approximately equal to the real portion of a zero sequence network representation that's commonly used in fault studies. Now, in terms of what we do about GICs, so a common mitigation strategy that's suggested is transformer neutral blockers. These don't impact the power carrying capacity of a power grid. However, they could impact ground fault relaying, which means that they're active devices and they're somewhat expensive, so we can't put them everywhere. And this motivates analysis and placement strategies in order to allocate them in a cost-effective way. And that motivates PowerModelsGMD. So this is a Julia jump package built on top of PowerModels infrastructure models, and includes a number of different analysis and mitigation formulations, as well as different relaxations, which include our full AC polar equations, as well as semi-definite programming, and second-order cone relaxations. We also can interface into not optimization solvers through the jump interface, or we do have our own custom matrix-based solvers when we're looking at getting a fast result, which I'm doing here. As far as what's our data model look like, so on the right we have our standard AC components, and then to that we add another set of so-called DC components. So we represent this as one single interconnected network. What do we need in order to solve this problem? So there's some additional information that's needed besides our usual AC input. So this includes substation locations, transformer winding configurations, and bus substation mappings. We're originally using a custom file format, although we've now moved to a semi-standard file format that's been developed under PSSE and is supported under other software packages. So what's this look like? Basically, it's a CSV-ish format, which is relatively easy to parse. Okay, and now that I'm almost done, here we have the analysis I promised. So this is a 500 bus synthetic case produced by the Texas A&M University, and we're applying a pretty hefty 10 volt per kilometer east-west field. And we use a screening criteria, like which of our transformers have a weighted neutral current over 100 amps. So this is what we got. Out of 131 total transformers, we only see that 13 have very high neutral currents. So this is actually kind of encouraging, and it's relatively similar to other studies. So while there's certainly a degree of exogenous uncertainty in here, so you don't want to take what I'm saying for completely trustworthy. Chances are, the power grid is probably going to be fine, and if you want to buy a Tesla, you're probably safe doing that. Okay, so GitHub repo is here, and I guess I can answer any questions folks have. Sure.
The actual test with these transformers to get them over 100 amps and see what happens to them?
Okay, yeah, so there's been, the question was, have transformers been tested over 100 amps to see what happens? And yes, there is some hardware testing and modeling. I believe that's done by Luis Marti et al. Any other questions? All right, cool. Thank you.